Why do you have two different equations for water? Because one of them is oxidation and one is reduction. Okay, so in the one case, the water is gaining electrons at the cathode, and in the other case, it's giving up electrons at the anodes. Okay, so it might be a little tricky trying to figure out what the chemistry is. Now, we're looking at this on a very superficial level, so the questions you might be expected to answer would be something like this. Given this information, what would happen here? I'd expect you could do what we just did. Or you might encounter something that says, this is the chemistry, do these calculations. And that's what we're going to look at now. So once we know the chemistry, we can calculate a lot of information about the electrolysis. We can get information about the amount of material being produced, and we can get information about the current that's being used to generate that. So we measure electrical current in amperes. We use the uppercase A. The charge is measured in coulombs. We already looked at this in terms of the Faraday constant, which was coulombs per mole of electrons, right? And remember, when we talk about this coulomb of charge, that is generated by a current of 1 amp running for 1 second. So a coulomb is an ampere second. So these are the definitions you have to remember. And remember, 1 volt is a joule per coulomb. So those are the things you kind of have to remember as we go forward here. So we can calculate the amperage, we can calculate the charge, we can calculate how much material is being produced, and those are things we're going to look at in the next couple pages of the notes. What's the charge generated by a 5 amp current flowing for 10 seconds? Well, the charge in coulombs is equal to the current times the time. And by definition, a coulomb of charge is an ampere second, so the charge in coulombs is equal to the current, 5 amps, times 10 seconds. It's equal to 50 ampere seconds, or 50 coulombs. So that's pretty straightforward calculating. You just have to remember the definition. Now, we've already introduced the Faraday constant. And the Faraday relates the charge to the number of electrons. So sometimes you'll hear people say 1 mole of electrons is equal to 1 Faraday. And we say that the Faraday is 9.65 times 10 to the 4th coulombs of charge per 1 mole of electrons. So how is this going to help us in electrolysis? Well, it's going to help us figure out how much material is being used up or prepared. So let's look at an example. How many grams of copper are deposited on the cathode of an electrolytic cell if we run an electric current of 2 amps through a solution of copper sulfate for a period of 2 minutes? Well, when we're dealing with electrolysis, we deal with half reactions a lot of the time, because we're looking at what's going on in 1/2 cell, either the cathode or the anode. So we start off thinking about, I have copper sulfate. That should be a lowercase u. So I have copper sulfate. It's going to go into solution and produce copper ions and sulfate ions. What if sulfate ions had anything to do with what we're talking about, galvanic cells and electrolysis up to this point? Nothing. So it's a spectator ion, so we ignore the sulfate. So the chemistry that's going on is the copper 2 plus 2 electrons gives me copper solid. Now you might say, well, how do I know the sulfate's an electron? Well, maybe you don't, but if you read this problem and it asks how much copper is being deposited, it doesn't say anything about sulfate, so that might be a clue you can ignore the sulfate. So now let's look at the relationship between the copper that's being produced and the electrons that it takes. We're used to looking at balanced equations and using the coefficients in balanced equations as part of our conversion factors. So we can write a conversion factor. 1 mole of copper is produced from 2 moles of electrons from our balanced equation. Now, since it asks about grams of copper, we say, well, where do we go when we need mass of something? We look at molar mass. So we grab the periodic chart. 1 mole of copper has a mass of 63.546 grams of copper. And now we're interested in 20 minutes, but our charge is in ampere seconds, so we need to know that 60 seconds is 1 minute. So that's all the information we have to either think of or look up or remember. Now we can take this information and we can calculate the charge that's being generated. The charge is equal to the amperage times the time in seconds. So the charge in coulombs is our 2 amp current running for 20 minutes. And we know that 60 seconds is 1 minute. So we get 2,400 ampere seconds, or 2,400 coulombs. Now, when I look at this, I had 3 sig figs in my amperage and my time. So this first 0 is significant. The second one is not. So we can either show that by drawing the bar over the 1 to say it's significant, or we could put it in scientific notation. So now we know how much charge was generated. Now we can relate the charge to the mass of copper doing a fence post kind of dimensional analysis, factor label, whatever you call it, calculation. So I know that I have 2,400 coulombs. I know that I know that 9.65 times 10 to the 4th coulombs generates 1 mole of electrons, so my coulombs cancel. I know that 2 moles of electrons generates 1 mole of copper. And I know that 1 mole of copper has a mass of 63.546 grams of copper. So I just have to take everything that I've been given or found and sort of put it all together to change the charge in coulombs into moles of copper goes into grams of copper, and I get 0.790 grams of copper. And this is the kind of calculations they do to coat things with metals using electrolysis. Electroplating is commonly done this way. Okay, here's one for you to try. Go ahead and do this at your boards with your group.